Hi folks, welcome back to Physics with Captain Rod. I'm making this video as kind of an introduction to concepts of angular velocity and angular acceleration. So let me talk about what we're looking at here. So imagine this large wheel or pulley fixed, free to rotate about an axis. And imagine this is a pretty massive pulley made of steel or iron or something like that. And then it's got this rope wound around it, attached to this rock or something like this. Now imagine that this rock is released. And for the sake of this example, let's assume it's released from rest. Now, as far as the rock is concerned, this is not a free fall situation because, we've got this extra force here, this tension acting up. But the rock, should accelerate down. So again, if this pulley here is relatively free of friction, the rock will accelerate down at some value. Now, the actual value is not important for the discussion. And what I want to focus on here for this video is what's actually happening to the pulley. So if I pick a point on the pulley, maybe this point right here, and I call it P. So this point is going to start moving along this path, and that point actually is going to accelerate as well. So if I were to do kind of like a little motion diagram for P, click, 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 to this point right here, and I'm going to call this maybe the initial position, and here's the final position. You notice there's an angle here, theta, that would be changing with time. So when the pulley's rotating and this angle is changing, the pulley now has what's called an angular velocity. And I've already went ahead and defined this up here. So angular velocity, this is how I define it. It's the rate that theta changes, where theta is an angle, some sort of angle used to measure I'll say the angular displacement of the body. So your angular velocity describes how fast this variable is changing. Now, like all rate of changes, right, here's how it can be calculated. So your average angular velocity, right, and this is supposed to be the Greek letter omega here, which most books I see used to represent angular velocity. I put a bar over it because what I'm about to talk about here is what's called your average angular velocity would be change in theta over change in time. Just like an average linear velocity that you learn about early on in physics might be something like delta x over delta t or delta y over delta t. Now, this would give the average angular velocity, and we can also write this in the language of derivatives. So d theta dt would give what's called your instantaneous angular velocity. All right, let's chat units. So angular velocity is typically measured in maybe rotation per minute or degree per minute or degree per hour, anything that describes a rotation or some sort of change in theta over a change in time. The gold standard in physics and in engineering is the radian per second. So the standard units on that, I'll put them over here in radian per second. So at this point, I'm going to take a moment here and kind of review the concept of a radian. So the radian comes from the concept of arc length. So this point P has traveled along this path, this green distance I'm going to call S. This interior angle in radians is defined as the ratio of S over R. So if you're not familiar with the radian, go back and watch some of my videos under trigonometry and where I talk about the radian. So this angle that I've drawn is roughly maybe 0.7 or 0.8 radians because my arc length here is about 70% of the radius. Now, the angular velocity as this thing rotates, right? So the angular velocity describes how fast it's rotating. So that's going to be the rate at which theta is changing. And angular velocity is a vector quantity. So let's talk about the direction now. The direction on an angular velocity is given by a right-hand rule. If I were to put a little set of coordinates here, x, y, and I'm going to go ahead and draw that third axis, the z-axis here. So if we look at a little set of coordinates like x, y, z, you notice this object is rotating about the z-axis. Now it's kind of hard to describe on this two-dimensional page here, but if you're watching this video, put your hand, I don't want to describe this here, if you take your right hand and you just kind of like mentally grab onto the z-axis, you'll notice that your fingers are rolling around in the direction of rotation. So this is how the angular velocity vector is determined for a rotating object. You just kind of mentally grab the object, so to speak, with your fingers rolling in the direction of rotation. Your thumb gives you the direction of the angular velocity vector. You'll notice here that your thumb should be pointing this way. And again, I will make another video here that's in a better format for talking about right-hand rule. So for now, I'm just going to say you apply right-hand rule. The angular velocity vector would be this way. In this example, that would be in the plus k direction. In most two-dimensional problems, clockwise or counterclockwise is good enough. Right. So now, let's talk a little bit about what that angular velocity is doing. Right. So in this example, we're just going to assume it starts from rest. Right. However, as time goes on, the rotation rate of this object is going to be rotating faster and faster and faster. So the angular velocity is increasing. So if I were to graph, and I've already started my picture here, if I were to graph angular velocity against time, again for this object, that might look something like this. Oops, let's do that in a different color. Now, you'll notice here that my angular velocity is changing, and anytime we have something that's changing, we can define a rate of change for it. And the rate at which your angular velocity changes is called angular acceleration. I like to define it like this. Angular acceleration is defined as rate that your angular velocity, I'm just going to put omega here, changes. Right. And here's how it's calculated. Your average, your average angular acceleration, this is the Greek letter alpha. Most books I see use the letter alpha to represent angular acceleration. So this would equal change in angular velocity over change in time. Or we could, in the language of derivatives, we can say that your angular acceleration or your instantaneous angular acceleration is the time rate of change of your angular velocity. Right, so if you're familiar with methods of calculus, these are, pay attention to these. If you're not, if you're somebody, you're watching this video and you haven't had a calculus course, that's okay. Just focus on, for now, these definitions or how they're calculated in terms of averages. Now units, since angular velocity is typically measured in radian per second, we're dividing that by time. So our units work out to radian per second or radian per second squared. All right. The direction of an angular acceleration vector is given again by right-hand rule. You'll notice that in this example, I'll just say this, the angular velocity vector is this way, about the z-axis. And in this case, the rotation rate is increasing, so the angular velocity, or I'm sorry, the angular acceleration is in the same direction. If this thing were rotating this way, however, the rotation rate were decreasing, then the angular acceleration would be the opposite direction. All right. I'm going to talk a little bit about calculations here now. Let's start with this. So if I take this equation and rearrange it, we can write it S is equal to R times theta. And this equation now, if we go ahead and time differentiate it, this is going to read S dot, which is a tangential velocity, is equal to R times theta dot. Right? And theta dot is what we call the angular velocity. So here's a relationship that tells us speed against angular rotation rate. Now, one thing I'd like to point out when I differentiated this, as this thing's moving in a circle, the point P here is moving in a circular path, and therefore the radius is not changing. So when we differentiate it, this the only derivative term that survives is the R theta dot. So this gives us a relationship for the tangential velocity against the rotation rate. If we time differentiate this again, this gives us a relationship for the tangential acceleration against the angular acceleration. Ooh, pardon me there. So again, if we differentiate this holding R constant, we would just have an R theta double dot, or that's what we call R times alpha. So These are the relationships here, here, and here for going back and forth between the translational motion quantities, which, the S would be measured in meters, V in meter per second, acceleration in meter per second squared, and the rotational quantities, where theta would be measured in radians, the angular velocity would be measured in radian per second, and the angular acceleration in radian per second squared. All right. Also, again, these equations are perfectly fine to use English units as well. I'll talk a little bit about the graph here now, as far as studying the kinematic motion of an object here. So when we have an angular velocity graph, it's useful for a couple of things. First, the slope gives the angular acceleration. And you'll notice if I take angular velocity times time, that's going to give me this area right here. Angular velocity times time is going to give me the change in theta, which will be a rotation rate. So I'm just going to say that your change in theta comes from area bound under the angular velocity curve. So a kinematic analysis of a rotational system is virtually identical to a kinematic analysis of a translational system. So if you're, in one of my classes previously in the semester, we talked about, writing equations that describe position and velocity of cars and things like that going down the road. And we use concepts of slope and area to write equations having to do with velocity, acceleration, and time. So we're going to do a similar type of thing here in my dynamics class for rotating objects. So this video is just meant to be kind of an introduction to angular velocity, angular acceleration, a little bit about how to go back and forth here between the translational variables like distance, velocity, and acceleration, and the rotational variables, angle, angular velocity, angular acceleration. A little bit here, just a tad or just a little touch into how to do kind of a kinematic analysis. Very similar to a translational motion problem. I'll usually start with an angular velocity graph against time and use concepts of slope and area to derive equations for acceleration and angular displacement. So again, I hope this video is a reasonable introduction into these concepts. Have a great day.